Good day, sir and classmates. Today I will be talking about structural steel design requirements. So first, the following load combinations shall be followed to their respective design method. And for the as shown in the left image, we have the load combinations for allowable strength design. And on the right, we have the factored loads for the load and resistance factor design. So we take note of this as we proceed to the design basis. So in the code, it mentioned two methods of design analysis. For allowable strength design, this uses unfactored load combinations. But as previously mentioned, the required strength is designed by elastic analysis, and the resulting value in this design is called allowable strength. To account for overload or understrength, a factor of safety is applied to reduce the nominal resistance of a structural member to a fraction of its tangible capacity. The general format for an allowable stress design has the form of this equation right here, where R sub A is the required strength. For load and resistance factor design, this uses factored load combinations or the ultimate load. The required strength works on the plastic region. This is where actual collapse or breakage of the members occur. And the resulting value in this design is called the ultimate or design strength. The theoretical strength of the member is reduced by the application of a resistance factor to its nominal strength, as seen in this equation. For the design for stability, it shall be determined in accordance with Section 503. This design considers any method, and as per the code, the direct analysis method is considered, and it has to influence, it considers the influence of the following. Second order effects, this has to do with the drift and deflection of the structure, flexural, shear, and axial deformations, geometric imperfections, and member stiffness reduction due to residual stresses on the stability of the structure. For design of connections, the connection element shall be designed in accordance with the provisions of sections 510 and 511. And it is mentioned that the required strength of the connection shall be determined by structural analysis for the specified design loads and shall be a proportion of the required strength of the connected members when specified. So there are two types of connections. First is a simple connection. This is designed as flexible, and flexible meaning the beam flanges are not rigidly connected to the column, it's free to rotate. So they are permitted to be proportioned for the reaction shears only. Flexible beam connections shall accommodate end rotations of simple beams. And the second type of connection is the moment connection, and it is designed for the combined effect of forces resulting from moment and shear induced by the rigidity of the connections. So here it will resist both shear and moment forces and cause a transfer of bending moment from member to member. This connection provides more lateral stability in steel frames, but this type of connection is more complex and costly. As you can see in the picture, for a simple connection, the web of the beam is bolted to the column, and it shows that it's not rigidly connected to the column as compared to the second picture, where the flanges and the web of the beam are welded to the column. For the design for serviceability, the overall structure that includes the individual members, connections, and connectors shall be checked for serviceability. It is evaluated using the appropriate load combinations for the serviceability limit states identified. So this design ensures that a structure is comfortable and usable for its occupants under normal usage. So we try to prevent excessive deflection, cracking, vibration, etc. It doesn't ask if the structure will fail, but whether it deflects too much that it makes it uncomfortable for the occupants. For design for ponding, the roof system is investigated through structural analysis to assure adequate strength and stability under ponding conditions, unless the roof system is provided to have a slope. on the roof surface that points toward a drainage system to prevent accumulation of water. So we can see here in this picture that there are drainage elements located along this edge of the roof, and we have a slope here, it's a roof, and that would prevent the accumulation of water. This design requirement is to prevent ponding deflection like what is shown in this figure. That's why it's important to consider design for ponding. Design for fatigue. This is considered for members and their connections subjected to repeated loading, because fatigue is a type of failure when the steel element is under repeated loading or stress. So fatigue is considered in accordance with Appendix A3, Design for Fatigue in NSCP 2015. For the design for fire conditions, the structure shall be capable of providing adequate strength and deformation capacity to withstand the structural actions developed during the fire within the prescribed limits of deformation. So one of the performance requirements is that the structure should maintain its load-bearing function under the design basis fire. It should also satisfy displacement constraints to maintain fire barrier and compartmentalization requirements. Satisfactory performance can be demonstrated by qualification testing or engineering analysis. The appendix also includes fire duration, fire protection systems, thermal expansion, several methods of analysis, and many more. For the design for corrosion effects, this deals with the possibility of the corrosion to damage the strength or serviceability of a structure. Thus, the structural members shall be designed to tolerate corrosion or to be protected against corrosion. So there are several treatments to prevent corrosion, and the image shows barrier coating and hot dip galvanization here. For the design wall thickness for hollow structural steel members, the design wall thickness T shall be used in calculations involving the wall thickness of hollow structural members. And the following equations are used depending on the type of pipe used, whether it's ERW or SAW. For the classifications of sections for local buckling, it is classified into three sections. First is the compact section, wherein the width-thickness ratio of its compression elements doesn't exceed the limiting width-thickness ratio lambda p. For non-compact, it's when the width-thickness ratio exceeds lambda p but does not exceed lambda r. And the slender element ratio is when the width-thickness ratio of any element exceeds lambda r. So we see in this image here, it's like a simplified version of like the difference between the three sections, and you can see that it becomes more slender as the width-thickness ratio increases. And here in this image, this shows local buckling of the steel members here and here. So for fabrication, erection, and quality control, shop drawings, fabrication, shop painting, erection, and quality control shall meet the requirements stipulated in section 513. And generally, fabrication talks about cambering, curving, straightening of steel, thermal cutting, welding techniques, bolt holes, etc. Erection deals with the alignment of column bases, bracing, bolts, welds, and base plates. Quality control talks about the quality control procedures, and this includes the inspection of welding and bolt connections. Thank you for listening.